All right, so let's get started. So hi, I'm T. Songjin Park, and welcome to the practice session week 9, which is the word-to-vec. So today we will cover the implementation of the word-to-vec, especially the skipgram. So starting from the tokenizer, and we will build the vocabulary, and then we will implement the skipgram and applying some negative sampling strategy on the skipgram. And in the next section, we will use some sentence piece library. So we will learn how to use some sentence piece packaging, and we will visualize the word-to-vec and the sentence piece results with the TSNE. And some take-home examples are both the tokenizer or some BPE. So similar to other practice session, if you have any question, please feel free to ask me. Right? So let's start from the word-to-vec. So in this section, we will implement the word-to-vec from very basic building block. So the first code block is just for importing some Python libraries, which we will use in this practice session. So just run the code like this. All right, so just run the code. And the first part of the section 1 is the implementation of the tokenizer. So in this section, we will implement the very basic tokenizer, which we call it as a white space tokenizer. So the tokenizer requires only 2 functionality. So first one is break the sentence into words whenever it encounters a white space character, and then returns the list of words. For example, as you can see here, so this sentence should be tokenized into I and M. Boy, something like this. And then the next requirement is 4 punctuation marks, which listed in here. So period and comma and exclamation mark, and the question mark will be the 4 punctuation marks, and they should be tokenized into the independent token, like hi and the period should be hi and the period. So this is the only requirement for the tokenizer. So I will give you 5 minutes to implement this function. Yeah, I will give you 5 minutes to implement this function. You can use the regular expression module, which is the library in the Python, or you can just use some Python native functions like replace or split or other things. It's also fine. So just feel free to implement the tokenizer in the various way. Oh, and also, if you finish the implementation of your tokenizer, just run the code in below, which is the test tokenize. And if you does well, then the code will output the test passed, just like this. And something goes wrong with your tokenizer, then it will output some type error or other things. All right, I will show you my solution. So I implement this function with the regular expression, especially the re library in the Python. So re.sub serves some similar job as an Python native function replace. So it replaced the for punctuation mark with the white space on the two left and the right side. And then it just split the word with the dot split native function. So this one is extremely simple. So I hope everyone implement this function without the difficulty. And let's move on to the next part. And the next part is building the vocabulary. So in this section, we will implement the function build vocab to build the vocabulary for the further use. So I wrote down some requirements of the build vocab function below. So the input arguments are the sentences and the min freq, which is the sentences as a list of sentences to build the vocab, and each sentence is a list of words, which is the output of the test. Tokenize, because we output the tokenize function. The tokenize function outputs the sentence with the list of words. So the input should be the list of words. And the min freq is the minimum frequency of the word. So words that have a frequency less than the threshold are excluded from the vocabulary. So this is because we trying to handle some rare words which occur some overfitting or some generalization issues in actual use. So we will exclude some rare words from the vocabulary. All right. So, and then the build vocab function should return 3 dictionary. So index to word is the map an index to word, and word to index is vice versa. So map the word to an index, and word frequency is counting the word, the occurrence of the word in the corpus. So yeah, so word freq means the word and its freq occurrence in the corpus. So you can see, you can check the key and the value here, and I will give you 5 minutes for the implementation. All right, so there's a question. Sorry, could you explain more detail about your question? 해나라님 그 질문을 혹시 조금 더 자세히 설명해 주실 수 있는지 지금 그 패드랑 언노운 인덱스가 왜 굳이 1이랑 0이 돼야 된다고 생각하시는지 조금 설명해 주실 수 있을까요? Right. In the meanwhile, you just run the below code, which is the test build block build vocab function, and if your code outputs something like this, then everything goes okay. So yeah, I believe everything goes okay. Oh, let me see. All right, sorry. So this is this is just an example. So yes, this could be this one if we strictly follows the example. Sorry. Just like this. Yeah, it does not matter much, but let's change the code like this. 네, 해나라님 감사합니다. Right, I will show you my solution. Yeah, so it's be simple. So I will explain only some important lines. So list and the chain with star means that it concatenates all the list of words into a single list. So this flattened list contains the words occur in the corpus, and we use the counter in the we use the counter function, which is in the collections library, which and it does that it counts the occurrence of the element in the list, and then it returns the dictionary. Key is the element, and the number of occurrence will be the value. And this is what we want. And then we filter the words which occur less than the word frequency. So this code does the work, and it is a bit simple, so I will not explain further. Oh, I see. So the question from the VG, what does the asterisk mean before the sentence mean? So I believe everyone saw something like this. And the single asterisk means it passed the argument with some in the order of the, so the asterisk means it passes the element of the sentences to this function chain with the order of element in the sentence. And two asterisks means that if the sentence is the dictionary, then it passed the argument as the name becomes a key, and then the value becomes the value of the dictionary. So I recommend you to search the meaning of the asterisk and the two asterisks, double asterisk in the Google, but the basic usage of the asterisk and the double asterisk is the one I explained. This is the one I explained. All right, thank you. All right. Lots of the functions are extremely simple. So let's move on to the skipgram. So in this section, we will implement the skipgram. So we also prepare some inputs for training the word2vec. So the first part is prepare the training data. So you can see the code block below. We will implement the function which returns the tuple of the center word and the surrounding word pair for the skipgram. So I'll explain more about the function and the example. So input arguments, the function receives two input arguments, which is the tokens and the window size. So window size is a number of the neighborhood. So as you can see that this figure has the window size, the example of the window size 3, which is that the center word includes the neighborhood, which is with the distance with the distance 3. So you can see that the 3 words in the both sides are included as a considered as a neighborhood of the center word. And this is the meaning of the win size. And the tokens arguments is a sentence where the center word and the surrounding word come from, and it is tokenized. So this is the list of the words, which is the list of string. And your job is to return the window pairs, which is the list of the tuple, and each tuple consists of the two words, which is first one is the center word and the second one is the surrounding word. So for example, let's start with the let us assume we have the function receives the sentence John's book is not popular, and the output should be the sliding the window from John's to the popular. So the first center word become the John's, and the neighbor of the John's with the distance 2, let assume the window size at 2, then the surrounding words become, there's no left side, so we only need to consider the right side. So the neighbor of the Johns become the book and is. So the output list should contain the Johns and the book and Johns and the is. And then we move on to the next center word, which is the book. And now the book become the center word, and the neighbor with the distance 2 should be John's and is and not. And you can see that the center word book has three tuples, tuple pair, three tuples as book and the John's, and book and the is, and book and a not. And move on to the next center word is, and so on. I think the example is a bit straightforward, so I believe everyone understand the requirement of the get window pair. So I'll give you 5 minutes for the implementation, and we will check the solution. No, all right, I will show you my solution again. Oh, by the way, we changed the template of the word to index and index to word to this way. Am I right? Yeah. This way, please. So add pad to the word to index and index to word. Actually, we does not use the pad for this practice session, but in the actual use of the tokenizer or some word embedding, you will use the pad token frequently because the length of sentence is differs per sample. By the way, if you want to learn more about the regular expression, then just go to the Google and search what is the regular expressions, or some keyword like regular expression cheat sheet like this one. And many people listed the regular expression just like this. So I will share this one to everyone. So if anyone wants to learn more about the regular expression. Right, so I will show you my solution. So this one is my implementation, and I implement just same as I explained above. So we first calculate the start and end index, and the start should be minimum 0. So we apply the max between 0 and index minus win size. And we also calculate the end, and the maximum of end should be lengths of the tokens list. So we apply the min function with the len tokens and the index plus win plus size. And the remaining job is just sliding from start to end and append this pair, which is the token is the center word, and tokens with the win index, which is we calculated here, is the index of the neighbor. So we just append the such pairs to the window pairs list. And everything goes okay. So I believe it's simple. So let's quickly move on to the next section. Right, sorry, wait, give me a minute. All right, so next part is preparing the data set, and especially we will implement the negative sampling function to improve the skipgram here. So the negative sampling function, the functionality of the negative sampling should be sampling the word from this probability distribution. So your job is to implement the prepare negative samples function, and the input argument is just a, let's see, all right, so input argument should be a power, which is this part, and the word frequency is which is the dictionary implemented above. I think it's located in here. So it counts the occurrence of the word in the corpus, and your job is to return the negative sample table. Return the set.negative sample table. Actually, it does not return the actual output, just assign the value to the attribute, something like this. Just fill the question mark. And this is the 1D NumPy array, which is filled with the vocabulary index. So we desire that the random sampling from this array is equivalent to sample the index from the distribution above. Yeah, this is the requirement, but actually, I believe you can just implement the negative sampler by using some np.random.choice function with the probability distribution follows this one. Is also fine. So this, I believe this is just one way to implement the negative sampling and sampling the negative sample from the distribution in the figure. So, but in this practice, just implement the 1D NumPy array, which is satisfy this requirement. All right, I'll give you 3 minutes for the implementation. And by the way, so there's no arguments word freak in here, and you just use self dot underbar word underbar freak as the same thing as the word freak input argument. I will directly show you the solution, and please try to implement the function yourself, but I believe this kind of implementation is not familiar to some of the students. So I just show you my solution until 11:10. All right, I'll explain about my solution. So before we go, I will briefly introduce the skipgram dataset class. So it has pad token and pad token index and unknown token index before as a value, and it initialized with the document window size, min, frig, and negative sampling, which means that documents is a list of sentence, which is equal to the corpus. So we use the tokenize function we implemented above to tokenize them into the list of words and then collect the tokens here. And then we also apply the build vocab function to tokens to calculate the index to word and word to index and word freak dictionary for the further use, and assign them with the underbar as the attribute of the class. And then if we turn on the negative sampling, then it constructs the negative sample table, and then prepare some items in there, and then we prepare the data for the further training. So that's it. So I'll explain my solution. So vocabulary size should be the length of the word freak, because the word freak dictionary contains all the words in here, and we set the power as 0.75, just like this figure. And then we calculate the norm, which is the power of the power and the account for count in the word of the word occurrence in the corpus. So you can see that this line is just equivalent to this one. And then we define the table here, and the table size should be table size just the arbitrary some large number. So I choose the this number, but you can just feel free to use any other numbers for the table size. It should be the only requirement is the large number. So, and then we assign the table as the filled with numpy array with the zeros. And then we add some elements to this table array, and you can see that we pop the word and the count sequentially from the word freak dictionary, and then until the cumulative probability reaches to this power of the count, which is the same as this one. We keep at the word index to the table, just like this one. And then if the P reaches to this probability, then we instantly terminate the while loop and then move on to the next word and the next occurrence of the word. And then we do this for all the word, and the table will be filled with the word index, and sampling from this list or numpy array is just same as sampling the word from this probability distribution. Approximately same as sampling from this distribution. All right, and then we assign the table to the self.negative sample table. And the negative sampler function does the random sampling from this table and prepare data. It's a bit long, but the functionality is simple. Return the center word, index of the center word and surrounding word, or if we turn on the negative sampling, then it returns the center word and surrounding word plus negative samples, sampled with 5 negative samples, which is k equal 5. That's the job here. And otherwise, this is just for call some important attributes. And this is the simple sample document, which I prepared here. Then just run this code block, and then also run this db equals skipgram dataset to define some dataset class for this one. And then, right, so the next part is training the skipgram without the negative sampling. So in this section, we will implement the objective function of the skipgram, and the objective function is the softmax over the center word and the surrounding word. So I believe everyone understand the objective function of the word to back. So your job is to implement the forward function here. Oh, sorry, this one is the solution. Yeah. Yeah, your job is to implement the forward function here, and I give you some mapping functions like input embedding and output embedding, which maps the input indices to the hidden latent dimension, and then the output embedding does the mapping from the latent vectors to the input indices. And otherwise, it receives the input features, which is the tuple. So center word indices should be the size of the batch size, and surrounding word indices should be the tensor with the shape batch size, and both are filled with the integer, and that's it. So I will give you 3 minutes for the implementation and we will check the solution. Please refer to the objective function here for the implementation. This will help you to implement the loss function. All right, I will show you my solution. So as I noted here. So input feature is a tuple of center word indices and the surrounding word indices. So I split them into two variables, and we first apply the mapping from indices to the latent space, which result the vector input embed, and then the matrix input embed, and we obtain the logic from matrix multiplying the input embed and the self dot output embedding. So ISM does the exactly same job as the torch.metmor or torch.mm sort of things. So you can use just the torch.mm or torch.metmor for to obtain the logic. So it maps the latent vectors to the output in index space. All right, and then the loss function is simply the cross entropy loss, and we calculate the loss with the logic and the target index, which is the surrounding word indices. All right, let's move on to the next code log, and you can see that running this code will resolve the decrement of the loss against the epoch, and it means our model at least works well. And the final objective of the section 1 is the implementation of skipgram with the negative sampling. So in this section, you will do the same thing as before, but add the negative sampling to the forward function. So you should consider everything is same as before. So input embedding and output embedding do the same thing, but the input feature is a bit different because center word indices is same as before, but surrounding word is a bit different because it is concatenated with the negative sample indices. So yeah, so the shape is the batch by the K, which we used in the above class, dataset class here. And the index of the surrounding word is always the 0. So please aware about the index 0 while you're implementing the function. So I'll give you also 3 minutes for the implementation. And everything is same, but the only difference is the surrounding words here also contains the negative sample indices. All right, this is my solution. So everything is same as before, but when we are doing some mapping from the latent space to the output in index space, we should aware that there's one more dimension in the input and the latent matrices, which is the number of negative samples plus the surrounding world, the ground truth surrounding world, which is thus it's J here, and then we apply the Betmol a little bit different way, so it results that the batch by and number of the negative words, it results in batch by number of negative words matrix, and then you apply the cross entropy loss here, and the result is that we know that the first element of the logit is the solution. So we apply the O0 as the label, and then we calculate the cross entropy loss here, and then it results the NCE word-to-vec training, and you can see that loss keep decreasing in the below section. All right, this is the end of the section 1, and I will very briefly introduce the section 2 because the sentence piece and the word-to-vec is bit very basic library for the server tokenizer or some learning some word embedding from the tokens. And I highly recommend you to use the Hugging Face tokenizers package because it provides many other functionalities, including tokenization or not just the tokenize the sentence into the tokens. It includes the training of the BPE or other some word piece tokenizer or adding some special tokens to the pre-trained model and etc. So I highly recommend you to use the Hugging Face tokenizers, and it provides some excellent tutorials in here, and it is not that hard. So I believe everyone can use this tokenizer without difficulty. But in this practice session, we cover some very basic libraries, which is the sentence piece, the Google released a year, 4 or 5 years ago, maybe. And then we also use some NLTK for tokenization and downloading the movie reviews dataset. All right, so the NLTK and some other word-to-vec pre-training. So the ZenSim provides some word-to-vec package function, which provides some So the GenSim.models include some word-to-vec function, a predefined word-to-vec function. And if you're using the word-to-vec function here, then you can train any kind of word-to-vec without the difficulty. And this does a similar work, which we implemented in the part 1. So I recommend you to use GenSim, the word-to-vec in the GenSim. And this is just setting the parameters. So the num feature should be the dimension of the embedding vector, and this one is the number of negative samples, and how to handle the rare word. We set the minimum word count should be 10, and the rarely occur less than 10 times should be treated as an unknown token, and we set the window size at 5, and downsampling is just same as the power in the equation of the negative sampling, and we set the epoch 5 and so on. This is just some details, so I just move on to the next code blocks. So in this code block, so I listed down how to use the sentence piece tokenizer library. It's very simple because we prepare the data and we put the strings into the data list, and then filtering them to with some strip and split, which yields some tokenized tokens will be put into the sentence naive list, and then just apply this function spm.sentencepiece-trainer, which builds some subword vocabulary from the corpus. So input should be trained text, includes the post.text and negative trained text. So this is just a text file which includes some entire corpus is passed to as an input, and other thing is just an configuration. So vocab size is the number of subwords in the sentence piece vocabulary. So you just feel free to set this one to not too small, not too large number, and then just run this command. Will automatically configure the some requirement in the sentence piece package. So this is just a detail, and also not many people use the sentence piece trainer nowadays. I believe almost everyone use the Hugging Face tokenizer, so I highly recommend to use this Hugging Face library. And this is just about how to use the GenSim. So you can train the word-to-vec with just simple configuration. And I will show you the visualization result. So let me see. This was just an example in some paper, which is written by Mikolov. And I also visualized the result of the word embeddings, which is trained with the Scatterplot in below. And you can see that actually, well, you cannot see some tendency here, but if you see this code block that which find the most similar word with the men, results the boy and women and doctor and some other words in the vocabulary. And you can see that boy and woman and something similar to the man is higher ranked on the list. So you can see that the word-to-vec package, word-to-vec function in the GenSim is trained well with the simple code block. Yeah, this is it. So I believe everyone just read the documentation of the GenSim and use it without the difficulty. And you can see that I also prepared the TSNE results of the subword. And actually, subword is a bit hard to interpret because this is each subword does not contain the much meaning, because it is not the entire word. So you can see that the tendency is a bit hard to capture in just in this figure, but yeah, you can train and visualize the subword tokenizer and the embedding of the subword, and then the TSNE of the subwords as I written down above. So please refer to such codes to rendering the TSNE and training the weight to back model with the on the corpus, and train the sentence piece tokenizer using the library from the Google. All right, that's it. So I believe time's up. So thank you for attending today's practice session. And if you have any question, please feel free to ask me via email or just leave the comments in the classroom. All right, thank you. So please feel free to leave the Zoom session. And if you have any further question, please feel free to ask me. 네, 감사합니다. 네, 질문 있으시면 자유롭게 해주셔도 괜찮을 것 같습니다. 한 2, 3분 정도 더 기다리다가 끝내도록 하겠습니다. Yep, thank you. Oh, there's a question from Singmin. Yeah, I will upload the completed solution onto Classroom, but difference is not that large. So anyway, I will upload the completed solution to the Classroom. 네, 감사합니다. 네, 그 프로젝트 1 마감은 다큐멘트에 적혀 있는 대로 네, 하시면 될 것 같습니다. 네, 감사합니다. 네, 다시 보여드리겠습니다. 아니야, 그건 그냥 시간이 남으실 때 한번 확인해 보시라고. 네, 그냥 테이크홈 example입니다. 그냥 편하게 뭐 제출해야 되거나 그런 건 아니고요. 그냥 자유롭게 그냥 뭐 보고 지나가시거나 아니면 사실 뭐 안 보셔도 됩니다. 그냥 이 허깅 페이스 토크나이저를 만약에 쓰게 되시면은 이때는 요 다큐멘트 정도는 조금 디테일하게 읽어보시면 도움이 많이 될 것 같습니다. 네, 뭐 근데 이게 요구사항이나 그런 건 아니고요. 네, 네, 감사합니다. 아, 네. 이 프로젝트 관련은 제가 이번 프로젝트는 담당 조교가 아니라서 혹시 클라썸에 문의를 해주시면은 그 담당 조교님이 좀 디테일하게 답변을 드릴 수 있을 것 같습니다. 네. 저는 이 채점 관련해서 아는 바가 크게 없어가지고, 네. All right. I think there's no more questions, so I will close the Zoom session. Thank you.